Okay, cool. Yeah, so hi everybody. My name is Fraser, and I'm going to be kicking off the demos by telling you guys about a project that I've been working on for the past 3 months here called Battle Rollup, which is a modular framework for building application-specific ZK rollups. So Justin just gave a really good story about living in a trillion gas world, but actually I'm going to tell you guys a solution to reduce gas fees, basically. So yeah, what's the motivation for this project? I mean, so this comes from a really controversial statement: on-chain games are good. Cool, probably no surprises there. Uh, Over the past few years, we've seen this amazing flurry of on-chain games which grant you a ton of affordances like composability, longevity, persistence, all of which you'll hear about today. But there is a problem with on-chain games, which is that, of course, they're super expensive to run on like mainnet Ethereum or even a sidechain or a rollup. But of course, like this isn't a problem with just roll. Oh, sorry. First of all, this is a tweet from Dark Forest just talking about how at their peak, their gas consumption was like greater than the consumption of all of Ethereum mainnet. So basically, we just don't want people to like pay $10 every time they want to move their character one tile. Okay, so yeah, it's not good. But yeah, this is not just a problem with games. Every application on Ethereum suffers from this problem with like hundreds of thousands of dollars paid in gas fees every day. And so to try and fix this, we've seen this industry spring up around the idea of like blockchain scaling solutions, most notably rollups. Okay, so you've probably heard of rollups. Here are some of them. You've probably heard of these before. Maybe some of those people are in the room right now. Um, when it comes to rollups, there's a real focus on the idea of EVM compatibility. So you can kind of think about rollups as like separate chains, but they try and replicate the experience of using Ethereum because everybody knows how to use Ethereum and there's like a wealth of developer tooling available for it. Cool. So those are rollups. I'll now try and give a sort of brief explanation of how they work. So as I mentioned, Ethereum block space is like super expensive. So we want to try and use the chain the least amount possible. And the idea is to try and use Ethereum as a highly secure real-time bulletin board. Basically, let's say that Alice here has some Ethereum on some layer 2 that she owns, and she wants to transfer that layer 2 Ethereum to her friend who's also on that layer 2. What she'll do is she'll sign a transaction saying that she wants to transfer the ETH, which you could think about as this post-it note, and she's going to stick this post-it note on the bulletin board that is Ethereum. And so over time, you sort of get this long list of events that everybody can see on Ethereum. We all have complete consensus on all of these inputs because they're on the world computer. It's like a big stream of bytes that everyone could agree on. And the cool thing is that with just these bytes, you could reconstruct the state of the rollup. You could basically, on your computer, you could like start the rollup from Genesis and then just iterate through all of these events, moving balances around, and you get the rollup state back. But obviously, it's not just enough to be able to know what the rollup state is in your head to just hallucinate it at home. You need to be able to prove that state back to layer 1. And the way that you prove this is basically you say you have some state of the rollup on layer 1 already, and you're going to take a batch of transactions and apply them to the current state and get some new state. So like, okay, here's the current state of the rollup, here's some more transactions, here's a new state. There's a couple of different ways of proving this. I prefer ZK, so that's all I'm going to talk about. So ZK rollups, they use this idea of validity proofs. So what happens here is that whoever it is that's going to report the state of the rollup to layer 1 has to provide a zero-knowledge proof that the state update they're proposing is actually valid. And then this zero-knowledge proof gets verified by a smart contract, and we can believe them. It's all just like cryptographic mathematical magic, completely trustless. This is not a super accurate graph for the ZK people, but the rough idea is that verifying these Stark proofs has like a constant cost, no matter how expensive the operation you're trying to verify is. So if you compute it on chain, it's going to be super expensive, but if you verify it with the Stark, it's always going to cost the same amount. So you kind of get a lot of bang for your buck. As I mentioned, there's a focus on EVM compatibility with rollups for a good reason, but actually EVM compatibility is like super hard. Like the EVM virtual machine was never designed for this sort of thing. and the code is long and it's very hard to verify. So one thing you might ask is like, do you actually need an entire EVM for all use cases? Oh, the projector's turned off. My laptop has not gone to sleep. I don't know what that is.
There we go.
Okay, cool. Yeah, so you might wonder, like, do we really need this? Because there's some applications that have a very clear pattern of use, don't really need to interact with other smart contracts. You can imagine, for instance, like a Uniswap rollup, where all you can do is trade on a DEX. Super simple. And proving the execution of a DEX, which I just couldn't fit onto this slide, is simpler than proving an entire VM. Cool. And so this is where you get the idea of application-specific rollups. Rollups are hyper-optimized to do one thing. And this was when I came to the residency, I wanted to work on something like this. So I decided to build a very simple rollup, what we call like a small rollup, that just processes payments. So you could deposit ETH into this rollup, transfer it around, and then withdraw it. So the way you think about it is that you have the very beefy, powerful EVM layer 2s, and then you have the cute battle rollup, which is not quite as powerful, but is very good at what it does. So the way this rollup worked was you had a smart contract where you could deposit ETH into the rollup. Then you could call the transfer function to transfer ETH around the rollup. But the key thing is that when people call the transfer function, we aren't updating any balances on chain. We just basically emit an event to say that they did that. And we sort of maintain this succinct commitment to the inputs. So this is not super important to know, but it's basically just like a hash of all the inputs that have happened so that when someone tries to make a proof, we can check if they're telling the truth and they've actually processed every event. So this is roughly how the lifespan of the rollup would look like. People deposit, people transfer. After a certain time span, the rollup gets frozen, so there's no more deposits. Somebody counts up the balances, generates a snark proof, and then calls settle to report the final state, which is everyone's final balances, back to layer 1. And then everyone can withdraw their monies. Great. So that was a fun project. It was actually a lot easier to do than I thought, but being at the Autonomous Worlds Residency, I wanted to try and put games on a rollup. How do you do that? So I mean, it's not as hard as you might think, right? You could have like a tic-tac-toe rollup. So people put their moves on layer 1. They say, hey, I want to move here. Put an X in the bottom right tile. We would just like figure out who the winner was off chain and then report that back to layer 1. This is where it came to my project that I'm going to demo today quickly, which is called Snark Tag, which is a real-time game of tag secured by Ethereum and Snark proofs. So I'll demo it soon, but I'll just quickly try and explain how it works. Basically, Snark Tag uses this kind of modular system of battle rollup. So there's these two systems called bulletin system and client system. Bulletin system is all like what it says in the tin. It's a highly secure, censorship-resistant bulletin board, codifying this idea of having a stream of bytes that we can all agree on. So people would put their take game actions and then put them onto the bulletin board. And then we have this idea of a client system, which is named after like a blockchain-like client. This might make sense to some people. Basically handles settlement. So the client system has its own copy of the rollup state. And then anytime somebody can come along and provide the new state of the rollup along with a ZK proof, and the client will just automatically update the state of the rollup. It's kind of like the client is just receiving snapshots of layer 2 all the time. And the client system and the inbox system work in tandem to make sure that provers are basically telling the truth. So the client system verifies proofs, and the built-in system gives the client data to check the provers like not lying. And that's all it is, really. You basically write a ZK circuit for your application that encodes the rules of that app. You deploy these two contracts, and you just have a rollup. So who's cute now? Yeah, so Snark Tag demo. This game is not super complicated, so I'll just show you guys a video kind of in the interests of the demo gods not breaking everything. So you play as like an abstract square. There's 3 of them, and they can basically fly around, collide with each other. The one that's colored red is kind of it, because it's a game of tag. So you see when this blue one hits the red one, they should swap. Yeah, so this guy's now it. What's happening here is that my actions are getting submitted on chain, and then locally I'm kind of computing the position of these squares and doing all these physics calculations, which again are encoded in the Stark circuit, which was kind of a crazy circuit if anybody wants to look at some point. So yeah, so that's the basic idea. I'll be running a playtest of the game this week. What are some next steps for Battle Rollup? I want to make deployment as easy as possible. So you should be able to just deploy a rollup with like one line of code, be super configurable. There's this notion of bundlers, which is a little bit like a rollup sequencer, where basically you could accumulate a batch of transactions off-chain and then post them to layer 1 all at once. This role would be completely permissionless, so this is not a centralized party. And I think if you combined it with EIP 4844, this would just like slash the fees of the rollup completely. And of course, I want to look at more advanced proving techniques like Nova, which would like really reduce the proving time for these recursive proofs I have to do to actually prove the state of the rollup. And yeah, so before I wrap up, I'll just pose a question to anyone who's building apps. Basically, I think when you're building an application, you have to try and think like, what is the minimum amount of gas to require to run this app without sacrificing any layer 1 security? Like the most gas-golfed application possible. And I think like looking at this curve again, where verifying Stark proofs is just a constant cost no matter what you're doing, basically. If your application is expensive enough, it almost always just makes sense to verify with the Stark. So, oh, sorry about that. Yeah, so if you find yourself at the top half of this curve, let's chat. And yeah, let's keep building a roll-up centric future.